Thanks for coming. Today I'm going to be talking about increasing high school students' opportunity to engage in proofs. Particularly, we're going to be talking about addressing the shortcomings of textbooks. So within textbooks, there exists variation of how proofs are being treated in high school curriculums. And why is it important? Most students, the mathematics they are exposed to is contained within the textbook, so it provides a structure of the mathematics they will eventually learn. Now, NCTM in the Principles and Standard highlighted that proofs should be taught across all grade levels. However, the reality is it's generally taught primarily in geometry. Additionally, Herbst documented that he highlighted that geometrical proofs, it transitioned from students just remembering it to actually having students construct proofs. Additionally, Donganue highlighted that if students want to learn to prove, it was primarily in the Pythagoras theorem or with constructing congruent polygons. So they were the general areas of where students learn to prove. In the American textbook, however, most researchers have documented that less than 5% of proofs within textbooks across the spectrum was devoted to proof. So Stylianides looked at the reform curriculum, and he looked at number theory, geometry, algebra, and he found 5%. Thompson, Sink, and Johnson, they look at algebra textbooks. Likewise, they found that less than 6% was devoted to developing reasoning and proof. This is indeed a concern because the low percentage of proofs in mathematics textbooks is not restricted solely to the United States. It's also been documented in Europe as well as in Canada. So students are not being provided the opportunity to prove within high school textbook curriculums. Now, with recent times, the Common Core state standards, many states have adopted it. And what I did was I actually just identified when proof occurred in the Common Core state standards. And it states, during high school, students begin to formalize experience from elementary and middle grades. More particularly, it's going to be happening in geometry. So the Common Core explicitly used the word proofs for the geometry courses. The requirement for students to be able to prove according to the document is very limited. In the sense, the document explicitly states students have to prove theorems involving similarities, laws of sign, circles, construct, inscribe geometrical theorems. In algebra, they just have to prove polynomial identities. And in functions, prove and apply trigonometric identities. Now, the limited attention given to proof in the Common Core state standards can have implication as to how it would be taught in the classroom, because what gets graded is what gets valued. And currently, this is primarily if they say what to prove. So if teachers are following the Common Core as a list of objectives, this can reduce the attention that will be given to proof during the instruction. So we need to start looking at how could we provide more opportunities for students to engage in proofs at the high school setting. Within textbooks, students are introduced to proofs via flow proofs, two-column proofs, paragraph proofs. Now, what's interesting is within the college environments, persons would normally write the paragraph proofs. However, within the high school setting, it's a two-column proof. So there's a shift in the way we introduce it at the high school level to the way it's expected to be written at the college level. Once again, this disconnect can have implications on what we're seeing at the college level. So for this talk, I'm going to differentiate between proof task and proof-related task. When I say proof task, the task explicitly requires them to write a proof or to complete a proof argument such that the finished products reflect a proof. So they can see a given, some form of argumentation to a concluding statement. When I say proof-related task, it provides the opportunity, may not necessarily be a proof. So because some students, when they say, oh, I identified congruent parts, that's a proof. Not necessarily, because it was not a constructed argument. So sometimes we have to differentiate, is it proof-related? It can provide the opportunity, but the question in and of itself is not necessarily a proof. So as I talk, I may be differentiating. So what I did was I started to look at these tasks carefully. And I looked at the level of cognitive demand from the work of Henderson Stein, but I decided to try to frame it for proofs within geometry textbooks. And I classified proofs in memorization, generally requiring students to complete skeletal proofs in which they had to fill in the blanks, or was very, very similar to the example 1, 2, and 3 within the textbook. So the student did not have to have any understanding of mathematics. Rather, if they look at example 1, they could just simply paste the same information and get the correct solution. So to me, it was fostering a form of memorizing of how to write that proof for that particular context. Procedures for connection, like they're matching statements together to say, okay, this go across, but it was almost like a random, they could just associate the terms. Sometimes the opportunity was provided for students to engage in why they're reasoning the way they do, but generally it was just more of a procedure. The procedures for connection includes items that require students to prove congruence of triangles, Cartesian planes using particular theorem, or require them to write a proof plan. Now, this was an interesting phenomenon because in some textbook, they gave the kids the proof plan and said, oh, take this proof plan and write a 2-column proof. So in that case, that would have been a procedure without any connection because they gave them all the information and they just wanted them to write it using a particular structure. And the doing mathematics. The doing mathematics required writing the complete proof, but it was not similar to tasks previously posed. So it could change the context, it could change representation, it was not algorithmic in nature. So some form of thinking was required. And so this is an example of what I consider to be very memorization, 2-column format. One strategy, fill in the blank. It was not abstract. So if the student had looked at the example in the book, the fill in the blank answers were identical to the example. So the student could have been successful on this task without understanding any mathematics. So it was more of a memorization task. This task, however, required what I classified as doing mathematics, in the sense that they're looking at one triangle, but there are actually 5 triangles operating all at the same time. So the students have to figure out how could they prove that VQ is congruent to SQ based on the given information. So now they're going to have to interpret which triangles they need to use to build this argument. The reality is tasks like this is seldom, if ever, posed within the high school environment. So the opportunity to prove is at doing mathematics level is seldom presented for students. I'm going to describe a study briefly that I analyzed textbooks, and I intentionally looked at the teacher's edition for chapters related to reasoning and proof, congruent triangles, and parallel and perpendicular lines, because the literature states if students were given the opportunity to prove, there would normally be the chapters that will be allocated for that region. Additionally, I coded the task based on what was written for the teachers as well as the students, because what teachers see, they can encourage students to do, because the teachers may be reading the book as a guide as to what is required. So I also look at the instruction they gave to the teachers. And I had multiple researchers assist with the coding of the level of cognitive demands, and generally we came to a common consensus as to the level of difficulty for those proofs to which students were exposed. So for the proof task, out of the 3 chapters, McDougal Littell posed 128 proof tasks. Prentice Hall, 79. So across 3 chapters, this is the maximum. When the proof was given, answers were reasoning provided most of the times. However, what's interesting was proofs were being labeled as challenge 27.8% of the time in Prentice Hall. When the task is labeled challenge, research have shown that teachers seldom pose challenge tasks because they want the kids to make math fun, and they also want to make math easy. So the notion of labeling a proof challenge, it also promotes a form of disposition that could be influencing students' willingness to learn to prove what teacher's teaching it. The proof, additionally, too, was always generally said in abstract situations. So students were not seeing the need for the proof. It was not practical, and they were proving things they already know to be true. So that was also something we had to take into consideration. So why do I need to prove it if I already know the solution to it? Fill in the blanks. Like I said, Prentice Hall had many fill-in-the-blank tasks. A lot of their proofs were memorization in nature, and it was composed of multiple parts. So they see in the proof as A, B, C, D, E, rather than seeing the proof as a complete argument. So the students would drive to say, oh, I could get 1 point or I could get 2 points without realizing it's a continuous nature of the argument that's important, rather than just getting a point. And so assessment is going to be a factor that could help us in increasing the opportunity to prove as well. Additionally, too, I looked at what representation they were seeing in the proofs. Now, in McDougal Littell, 2-column proofs were generally the primarily proof used. However, in the Prentice Hall geometry, paragraph and 2-column proofs were visible in both cases. This is interesting, especially when they go into college-level mathematics, 2 column proofs is not visible in most college-level math textbooks. So students, like I asked my pre-service teachers about proofs, and they admitted they're not ready to teach proof. The researchers, they were saying they're not ready to teach proof because the proof they're doing in college is not what they learn in high school, and they're just not ready for it. It's beyond their level of knowledge. And that's something for us to start thinking about. How are we introducing it, and how are we connecting it from the math in the high school to the math at the college level? Additionally, too, you realize that most of the proof students in the Prentice Hall were being introduced to are just more fill-in-the-blank and very low-level proofs. However, in the McDougal Littell, they provided more opportunities for students to construct complete proof arguments. So this result is interesting because it suggests that pending the textbook the student is using, their experience to proving can vary. And so as teachers, we can't change, we may not be able to make a decision on which textbook our school adopts, but we can make a decision about how we're going to implement our practices. So today I made a suggestion as to how could we address the shortcoming of the textbooks. The first thing I suggest is we need to modify the task. The reality is the textbook may not do it, so we need to find creative ways of providing opportunities for kids to engage in the act of constructing viable arguments. Perhaps we can find counterexamples. We could allow them to investigate conjectures, make conjectures, develop their argument, evaluate their arguments and correct the mistakes in the reasoning, as well as integrate such tasks into the assessment. I must reiterate, if proof, because when I interviewed the teacher said, oh, well, proof is seldom integrated in assessment. And if they do integrate proof in assessment, it's only the fill-in-the-blank task. So that's why we only teach those, because we want our kids to do well on the tests. So assessment was becoming a factor to the type of proofs the students were being exposed to. What gets graded is what gets valued. So if proof is not being assessed, then the value for it could be decreased. So perhaps we need to figure out how could we increase the opportunity for students to prove during assessment. Additionally, we can provide students with sample proofs that they have to evaluate. Having students evaluate the validity of the proof can help them reflect on what needs to be included such that the arguments are complete, as well as observe different ways proofs can be written. Finally, teachers, we need to plan accordingly. Reason being, we have to plan questions that we can actually ask students. And we have to consider the ways to orchestrate the discourse to facilitate the opportunity to prove. So detailed planning is needed to ensure that students are provided the opportunity to engage in proofs. The selection of tasks and deciding how to unpack those tasks during the enacted lesson require thought if the task had to be done meaningfully, and also for students to engage with them. Sometimes, like pending your mathematical knowledge, because one of the teachers I interviewed highlighted that, oh, she wasn't comfortable with proofs, so she would always ask her colleagues and watch her colleagues, and then she would mirror whatever they do within her classroom. So planning with a team can be beneficial. So you probably can ask your colleagues, could you look at this, get feedback on it, but you must be willing to get, open for criticism, open for improvement. And finally, we also must intentionally pose proof tasks that require some degree of thinking, such that the students can see the need for the proof. Now, this is the hardest part because we all want to make kids think math is easy and math is fun, but we must provide opportunity for rigor, for them to reflect. And mathematicians can tell you finding a solution to a new problem may not happen in 2 minutes. Most of the proofs the students see is completed within 2 minutes. So we perhaps need to expand the opportunity for them to say, okay, how could we reason to it? And help them to realize that sometimes proofs cannot be solved in such a short period of time. So we need to intentionally plan accordingly to provide those opportunities to prove. Thank you. Good on time? All right. Questions, comments, concerns? Okay.
Well, my question is, do you currently teach in the high school setting, and what are some methods that you use to modify to kind of help the inquiry-based learning in the high school setting?
Okay, good. I was a high school teacher, and currently I'm a teacher educator at the University of South Florida. So at IBL, to promote inquiry-based learning for teachers, we actually give them typical problems that students would actually solve. We start with fractions, because fractions, most persons know how to solve a fraction procedurally, but do they conceptualize why it works? And you allow them to consider, okay, why is it working? Why are we adding if the denominators are different? How did we come to decide a common denominator? For them to explore it and to provide their reasoning. Additionally, as a coordinator for the intermediate algebra program at the University of South Florida, I'm currently teaching the intermediate algebra. Because intermediate algebra, most students struggle, or it's more of a remedial course before they get ready to college algebra. And what I do is I intentionally pose an open question and said, okay, how would you solve it? Or I would put a wrong answer on the board and said, is this right? How would I fix it? Why would I do that? Why would I make these changes? So you allow them to be a part of the discourse to see how do they conceptualize the mathematics. So being a teacher educator as well as a teacher for mathematics for remedial students at the University of South Florida, I provide many opportunities for them to always reflect and see the bigger picture. But like I said, it's planning the time to do it, because the question is depth versus width. You may have a lot of things to cover, but are you covering it well? Question?
Do you see merit in two-column proofs at the high school stage? Do you see something in that that helps them to develop proof thinking?
I can see potential benefits, and I can also see potential limitations. The benefits is it helps them to see there is a logical flow from a given to a conclusion. The limitation, however, it may make students think proof is linearly, and they may think it's a one-way solution. So when teachers are evaluating it, for example, I saw a teacher mark a student answer wrong when lines 2 and 3 were interchanged because they wanted it a correct way without realizing the student had conceptualized the right argument. So in that case, it could be a hindrance to students developing their understanding of proof. But for students who are just starting to see it, it can be a form of an introductory method, but it can't just be the rigid format being employed.
The proof-related tasks, or the proof tasks that you had listed that were in the textbook that you were coding, were those all just prove this? I mean, is that what the instructions were, or were there any aspects of actually finding counterexamples or dealing with uncertainty where, is this statement true or false?
Yes. They had examples in chapter 2, like 2.1, if you look at reasoning approved chapter for finding counterexample. But like I said, it was so superficial in nature because the counterexamples were, can dogs fly? Or there are 579 days of the year. So the answer was very elementary in nature. So kids didn't have to think about cases of the counterexample being true or false. Versus if they found cases where some cases have worked, but not all, you seldom see those situations. So the counterexample, seeing it, and so I interviewed pre-service teachers about their proof schemes, and one teacher literally said, oh, a counterexample is not enough to say that the proof is incorrect. So that raised flags about the certainty of what a counterexample serves in her understanding of what a proof is.
What other categories besides proof tasks were the categories that you were distinguishing that from? And then secondly, are there any textbooks or textbook series that do have a stronger theme of proof in them besides the two that you evaluated?
Well, what I did is I coded the textbook as a whole, the chapters 2, 3, and 4. So I looked at the general the mathematical tasks themselves, and then I isolated the proof task because I'm aware that teachers have to teach a breadth of content area. So for the breadth of content area, Prentice Hall had a more high-level task. But when I focused only on the proof, their attention was less. But once again, like in their introduction, they state the goal of the textbook is to prepare them to be successful on assessment. And based on the teacher's feedback, proof is not assessed. And so once again, why pay attention to it in great detail if it's not going to be heavily assessed at the end of the day? So holistically, we need proofs. Realistically, it's not the center at this time. Hopefully with the standards for mathematical practice, which suggest we promote constructing viable arguments and engage in reasoning, teachers are now going to be considering ways to promote these opportunities for kids to prove and also just reflect on reasoning, even if they don't construct complete proof arguments. So, as it relates to other textbooks, I've been looking at other textbooks, but each of them have strengths and limitations because the textbook serves more of a goal, like I said, pending the teacher's mathematical knowledge. Teachers read the textbook, and if you're holding on to it very closely, it may not address enough. So I told them sometimes you may supplement it, sometimes you may just find other resources. And I also started looking at what were happening at the college level as well, like what textbook they were using. So like the bridge to abstract algebra or the bridge to proof or introductory to proof, they were using, you know, just considering starting with the counter example and building a way up. And then there's a book called What Secondary Teachers Need to Know About Mathematics. It started off with induction and proof, and that was the first chapter. And so when I read it, I was like, oh, this is interesting. But then the teachers wanted more. They wanted, I need a book. And I don't want to recommend a book. I want them to be resourceful to ensure that they can pull from multiple sources. Because once you recommend a book, you're once again restricting the lens in which you're looking through.